We've learned that we can find out a polynomial's factorability using the discriminant. We're now going to take a look at how some polynomials can be factored just by recognizing some patterns. Let's start by analyzing this simple polynomial, x² minus 9. By looking at it, we can see it has the form of a binomial. But it's not a normal looking binomial because it has a degree 2 term. Can we factor a binomial out of a binomial? Let's try imagining that this binomial is a trinomial with the b coefficient equal to 0, x² plus 0x minus 9. Can we factor a trinomial like this? Let's find out using the factorization theorem. Using b² minus 4ac, we get 0² minus 4 times 1 times negative 9, which equals 0 minus 4 times negative 9, which equals 36. Since the square root of 36 equals 6, our discriminant is a perfect square, and our trinomial is factorable over the integers. We can work with this. We need factors of negative 9 that sum up to 0. Summing up to 0 will be simple. Recall the inverse property of addition. When any number is summed with its inverse, it becomes 0. Therefore, we need a factor of negative 9 that produces a number and the inverse of that same number. Let's look at the factors. Negative 1, 9, 1, negative 9, negative 3, 3. The third set of factors contains an integer and its inverse. That set will sum to 0. Rewriting our polynomial gives us x² plus 3x minus 3x minus 9. We're now going to factor by grouping. X times x plus 3 minus 3 times x plus 3, which equals x minus 3 times x plus 3. Take a look at the binomial product that we produced and the original polynomial. Our polynomial had a second term that was a perfect square. The two constant terms are inverses of the factors of our perfect square. This leads us to a definition. The factors of the difference of two perfect squares. a² minus b² equals a minus b times a plus b. What this states is that when you have a difference of two squares, a² minus b², that includes coefficients and variables, this binomial can be factored as the product of two binomials. The root of the first term minus the root of the second term times the root of the first term plus the root of the second term. How can you know any of this is true? Let's prove it. Look at a² minus b². We'll use this to prove that we can factor binomials like this. Let's use the same techniques used in the last example to factor this. a² minus b² equals a² plus 0 times ab minus b². Remember that after factoring, the middle term has a factor from a and a factor from b. Thus, we used a times b as the variable term here. Now we're also going to factor this as if it's a trinomial with a not equal to 1. Thus, the factors of a² b² that sum up to 0ab are ab and negative ab. Thus, we have a² plus ab minus ab minus b². Using grouping, we have a times a plus b minus b times a plus b, which equals a minus b times a plus b. Let's work out a few practice problems. Number 1, x² minus 121. We know this is a difference of two perfect squares because the square root of 1 equals 1 and the square root of 121 equals 11. Therefore, the binomial factors like thus: x minus 11 times x plus 11. It's as simple as that. No trial and error factoring, no grouping, not even using the factorization theorem is required because we know that a difference of two perfect squares is automatically factorable over the integers thanks to our proof. Number 2, 25x² times 49. This time, we have a coefficient on the leading term. That's okay because the square root of 25 equals 5 and the square root of 49 equals 7. Therefore, our binomial product is 5x minus 7 times 5x plus 7. It's a good time to take another look at what's happening again. If we use FOIL on our product, 25x² plus 35x minus 35x minus 49, notice that the two middle terms are the same, just with different signs, 35x minus 35x. The inverse property of addition states that a number summed with its inverse is equal to 0. That's why we get a binomial even after multiplying two binomials. That's the pattern with the difference of two perfect squares. Number 3, 9x² minus 16y². Each term here has a coefficient and a variable. The two terms are perfect squares because the square root of 9 equals 3 and the square root of 16 equals 4. It doesn't matter that the second term has a variable with it. Notice that it is squared along with its coefficient. We could just as easily rewrite the binomial as 3x² minus 4y². As a matter of fact, rewriting our binomial like this helps us immensely in seeing how our factored product will look. 3x minus 4y times 3x plus 4y. We have seen that we can use patterns to help lighten our workload when factoring polynomials as well as multiplying them. There are two more patterns I'd like to go over, so stay tuned.